So before we move on to next block, I just wanted to check that there are a few questions, so I want to try to answer very quickly. One is Ray. Ray was asking how is the energy flow chart Sankey diagram for Australia, given that there is lots of cooling. That's where it's interesting. I mean, there is actually, if you look at Victoria, well, not today. It's a great day, but obviously winter is a bit. It's cold in other countries, in other states, and similarly for Tasmania and so Australia. Victoria also has got quite an extensive gas network that for space heating. So I think the Sankey diagram looks pretty similar. When you look at cooling, yes, basically instead of having heating, you have cooling. And you have a very similar Sankey diagram looking at the sort of residential sector. However, the interesting thing of Australia is that if you look at the Sankey diagram, majority of outputs are actually exports in terms of fuel, can be like coal or gas. Actually, it's lots of exports, which it's not like this in the UK. In the UK, you got imports and low domestic consumption. Australia instead produces so many resources and then exports resources. Again, particularly coal and gas, but also like nuclear resources, uranium. And that is again motivating in a way the discussions about let's move on from an economy that is based on exporting fossil fuels to an economy where we export clean energy, for example, in terms of hydrogen. And again, it's very much coming from Sankey diagram. So again, Sankey diagram is really a very powerful tool from a system level perspective to understand strategic directions of energy policy and also engineering infrastructure developments. And by the way, many of the discussions that we're having here in terms of gas, electricity, heat, cooling, by the way, again, it's just the same. It just instead of injecting heat into a house, extract heat, but the modeling is very similar. So what Carmen presented for an electric heat pump for heating can be adapted for cooling. So you can just take the notebook and change it slightly and model cooling instead. Would be very relevant to again to Australian case. But besides that, I say when you look at gas in particular in the future, we're more and more discussing hydrogen potential, and actually can be again adapted to see how hydrogen could be part of the big picture. And actually, we'll see something later about that. So this was for Ray in terms of Sankey diagram of Australia. Peter Kirby was asking about these node operating envelopes in different ways, how important it is to forecast these envelopes, for example, they are ahead for distribution network management. There's a great question. Think again in the project edge, what we're doing is we're exploring exactly this kind of requirements. So say you do it day ahead, then there may be what is the uncertainty, what is the cost for the market, be uncertain in the way that you create these operating envelopes. That what is nodal, that is sort of summarizing the potential, can also be at the level of the resources. These are the operating envelopes that Nando was presenting on Wednesday. However, uncertainty will play a role there. In the project edge that I mentioned a couple of times, we'll actually assess this. We'll also assess, for example, how frequent one would like to calculate the operating envelopes, because, for example, it is bringing value and dealing with uncertainty. There are other techniques that could be employed, similar to what Maria presented yesterday. For example, ideas such as use of this probabilistic modeling to actually assess the uncertainty around these operating envelopes. There is actually quite some nice publication available in IEEE transactions. However, they're not so specific about modeling of flexibility. There was a question was coming from Jamie. I think was keen to have this question answered. So, what assumptions are on the physical resources are you making when doing the Minkowski sum? Can the resources really all actuate in the direction you want at the time that you want? And do you model the network power losses between aggregated resources or assume it is negligible? Okay, that's all great question. So Jamie, the answer is you model everything that you can. So in the general model, if you read the paper, if in fact the model is including everything, is like whatever constraints are on a resource, can be ramping constraints, can be, for example, minimum stable generation constraints and all that. All of this can actually be incorporated in the mathematical model, because then the aggregation of the formulation of the operating envelopes and everything else is really an optimal power flow. And then if it's decoupled, if it's coupled across time steps, it's basically an intertemporal optimal power flow. But the mathematical model can actually capture all the details of the constraints. So if you can actually move in that direction at that speed and so on, the moment that you put those constraints in the mathematical model, because the physical resource can only do something, the model will capture it. And then it depends on what kind of optimal power flow model you use. If you use a full optimal, a full ACOPF, or for example, a relaxation, an SDP or SOC relaxation that as Stephen was presenting, then you will also be able to capture losses and, of course, other potential aspects. So it's all in the model that you have in the specifics of the algorithms you use. However, the formulation has been designed to be able to incorporate everything. And then happy to discuss more details if you wish. And then maybe there were a couple of questions. I think Peter Wong and Mark D were asking about thermal storage. Is it worth or not? So Peter was asking whether in the cost function we should also have capital investment. Yeah. So Peter, the notebook that the Carmen presented was really to show the operation. So operational flexibility in the system with or without thermal storage, really to illustrate how multi-energy flexibility effectively corresponds to electricity flexibility. Of course, if you then want to assess whether that is viable, what you would do is you would just run the operational problem for a given number of instances, temporal instances, and then you would perform cost-benefit analysis, including the investment. But the model, the operational model is still valid. You can just run that model for many instances, and then you have costs, revenues, savings in case, and then you weigh against the cost of investment. And MACD, I think that is also answering your question. Effectively, is it worth or not? Only a cost-benefit analysis can tell you. However, flexibility, certainly it is bringing lots of flexibility. And from my experience, in countries where actually you need substantial heating, for example, in the UK, but probably also in Victoria to a large extent, there is lots of flexibility that thermal storage can bring, and it's very, very cheap compared to, for example, having a battery, but it can bring very substantial benefits. There's a paper that is somehow, I'm not sure where we cited it, with Nick Good, that we look at the performance of a community energy system with electrical batteries and thermal storage. And clearly you see the thermal storage can do lots of things. Maybe in terms of pressure performance, not as good as a battery. But when you look at the cost, because it's a hot water tank, basically it's a fraction of what a battery would cost even now with costs going down. So yeah, thanks a lot for these questions. Please just keep asking. If I can't answer now, again I will answer later in Canvas. So I think it's time to move on now to the third block. So let me share screen again, and I will try to be. So this is the third block. And what we're talking about now is more specific about the flexibility coming from buildings, and then when you aggregate this in districts / communities, what kind of benefits and other considerations you need to make. And we will also mention very briefly, because I would like to focus on other aspects, this integrated optimal power flow, where you perform an OPF across different networks, not only electricity. But starting with understanding building flexibility, we have this kind of generation, solar PV. How much flexibility do we have coming from solar PV? Very, very limited. Effectively, you can curtail it in case, you can modulate a bit reactive power, but it's not too much flexibility that you have. That's why we introduce electrical storage. We use batteries, so that once you couple PV and batteries, actually you increase greatly the flexibility is available. And now that you learned about Minkowski sums and everything else, you can actually do it as an exercise, try to understand how is the flexibility of PV only, when flexibility is coming from curtailment and reactive power modulation. With respect to, for example, storage only, you only have a battery, no PV, and then you have both for a given load. What kind of flexibility you have? By the way, we'll do a small exercise later on. Then, of course, there is what we haven't shown too much is the flexibility on the demand side, looking at the electricity load. And there are different ways of doing it. For example, you can shift dishwasher, washing machines in time. You can curtail the services. You can switch off the electricity services. Of course, you can substitute for another energy vector that is again linked to the multi-energy flexibility. And just on that, this is basically called energy multi-energy input arbitrage, where again you look at the general mathematical model of this, and imagine you have an electric heat pump and a boiler that potentially could supply the heat demand addition to the electricity demand. So what happens is that depending on the prices of electricity with respect to gas, or depending on the outdoor temperature, you may decide to go for one or the other. So this is a typical scheme that, for example, is being discussed a lot in the UK as a hybrid heat pump, where effectively you will use an electric heat pump most of the time. However, when it's really cold in winter, with temperatures in degrees Celsius, negative, even very negative, you go to Scotland, a place like -10, even -15. Basically, heat pump performance are very, very poor. Talk about air source heat pump. Ground source has got other issues there. There's not enough space to put ground source heat pumps, especially in urban areas. So an air source heat pump at -5, -10 performs very, very poorly, especially air resistive heating. Therefore, in order to meet the electricity demand, the heat demand when it's really cold, you will need a gigantic heat pump with a massive impact on the bill, on the electricity infrastructure, and all that. So it may be more beneficial actually to introduce a small auxiliary boiler to top up the electric heat pump when it's really cold. It's kind of dual fuel hybrid heat pump. And when you look at, for example, some studies we did some time ago, you clearly see, for example, that having the gas boiler as a top up in this hybrid system effectively can save very, very substantial sort of peaking requirements on the electricity system. For example, we're moving from something like 88 gigawatt to 68 gigawatts. So it was like 20 gigawatts less of peaking generation we need in the UK system in that case, out of not even 100. So very substantial, like 25% less peaking generation because you have this dual fuel heat pump. Of course, that poses other questions like what happens to the utilization of the gas network when you only use the heat pump for a limited amount of time. Again, that's why it's a complex Techno-Economic problem. It's not about only the technical problem. There's also the idea of curtailing demand. Again, you curtail electricity demand. You can curtail pure electricity demand. For example, you can switch off TV. We will discuss this later if you really want and when you want to switch off the TV. Otherwise, if you are again in a multi-energy context, then your electricity demand is coupled to the production of heat, or as we said before, cooling. So everything I'm saying here for the ones that would like to apply this in a more straightforward way to Australia, it still applies. Just instead of producing heat, you produce cooling with a heat pump. You have a split system just behind me. I don't know if you can see my split system up there. Actually, that's basically never used for heating because there is gas it's using for cooling. The model is exactly the same. You take Carmen's notebook we're going to share, you change a couple of things, you do it for cooling, here you go, ready for Australia. Now, what can you do by switching off, by curtailment, your heating or cooling in a building when you are using an electricity supply for your heat pump, split system, and all that? Obviously, when you do that, you are affecting the indoor temperature. Therefore, your comfort level is changing. So that's why we talk about comfort to power arbitrage, because effectively you switch off your heat pump for cooling. For example, in summer, the temperature in the building goes up. You're giving up comfort level. So you're arbitraging from comfort to power. So you're gaining power savings, but you're losing comfort. The other way I look at this is the fact that you can only do this because there is a certain virtual energy storage level intrinsic in the building fabric that basically enables the thermal inertia of the building to slow down the changes in the temperature. So it doesn't go down like this from, I don't know, or up if it's about cooling, but actually it takes quite some time. So that constant, that time constant, depends on the thermal inertia of the building, and it is a form of energy storage. So it is thermal storage. However, it is virtual energy storage when you look at the electricity perspective, because as we were saying, in a multi-energy system context, it allows flexibility on the electricity side. And in fact, when you model it, as Carmen was showing in the notebook before, you see that in the model of the building, and by the way, there wasn't the full model as Carmen highlighted, also those kind of spikes that you saw in heat production or that. If you have the full model of the building, the model we used was a reduced model, basically only one time constant and no emitter and all that. The moment that you start having all the proper time constants, the model of the emitter, especially if you use a hydronic system, you don't see those spikes. And that's exactly because this all adds buffers, all adds virtual storages. So it's like thermal storage that it's in hot water, is in the fabric of the building, that, and this is modeled by all these capacitances, these thermal capacitances here in the equivalent model. However, it is projected onto what you can do in terms of flexibility on the electricity side. And in fact, in this case, what Carmen showed before, this was basically have a heat pump and a thermal storage, and it adds a buffer, and then you don't have these spikes and all that. Imagine that instead of this, you actually operate with your building, and instead of having hot water as a physical store, you now have the air and the building thermal inertia. What can you do with this is actually really operating your building as a virtual battery. So how do you do this? Imagine that you have a baseline consumption of your building. So this is actually taken from a commercial building in London. This is sort of realistic case. It's done with modeling, but then we were really doing for a proper demand response study in London again, like, probably 2009, 12 years ago. That was, long ago, but things haven't changed much. So what you do is, like, imagine you have a demand, a baseline consumption for your air conditioning system in this commercial building, probably for cooling. Yes, also London requires some cooling sometimes. And then what you do is you want to switch it off. Then you switch it off because you rely on thermal inertia, the temperature doesn't go up too much. This switching off, if in relative terms, if you compare to the baseline, switching off your air conditioning system for a certain time is equivalent to discharging electricity into the system. Look, if you are the electricity system, if you are a battery, and at a certain point the battery discharges electricity, or if you are consuming electricity and you stop consuming electricity, it does, for the electricity system, from the flexibility perspective, seen upstream, there is no difference. injecting power from a battery or switching off power is the same. So in this sense, this is a virtual battery is discharging. However, as a real battery, you need to recharge your system, right? Because now, as we discussed, because you are arbitraging between comfort and power, you discharge energy, so you do not consume energy, but your temperature is going up because the power you're using for cooling is no longer there. So your temperature goes up. Now, when you start again your air conditioning system, you want to bring down again your temperature, and depending on the type of air conditioning system you have, especially if it's a complex HVAC system in a commercial building, what will happen is that you will start pumping all your fans and everything else at full capacity, so that the actual consumption will spike above the original baseline. Because when you're moving on a relatively flat baseline, you are just modulate, especially with the modern HVAC, you just keep modulating how much power different compressors need and fans and so on. Instead, if you are a little bit more brutal, like switch off, switch on, and then you want to control your temperature like this, because it's valuable to do this because you're providing, for example, a frequency response service that is needed, then you can have this more extreme variation. So if you think about it, again, because we are comparing this with respect to the baseline, now you are charging your battery. So before you discharge, so you're building discharge energy, now your building is being recharged, exactly like a battery would do. The only difference is that with the battery, you can probably recharge after a few hours. So that, of course, the battery's got more flexibility because of this. With the building, you need to do it immediately afterwards because of the physics of the building. So this energy payback that you see, there is a component that is measured in terms of power, a component is measured in terms of energy. And if you are interested in this, there is this very nice paper that Ling Ji, one of my researchers, wrote a couple years ago on building to grid the flexibility, where it really describes all this behavior and the different metrics that you can use in terms of power, in terms of energy, to really model this kind of behavior. Now, what is particularly interesting in this virtual battery? If I ask you, basically here you are discharging, here you are charging. So if I ask you, what is the efficiency of this battery? What would you tell me? How much is, if you look at these figures, this figure and these areas, what is the efficiency of this battery? Yeah, efficiency is high. It's good feature. Yeah, but it's more than high. This efficiency is magic. It's almost defying the laws of physics. Yes, yes, Anthony. Good answer. So it is 300%. I think you've seen my lecture before, perhaps, Anthony. So you're cheating, or maybe not. A good answer anyway. So the effectively, as you can see now, what is efficiency is output divided by input, right? So what is the output here? You are discharging. This is the service you are providing. So the discharge is actually much bigger than the charging. So it is effectively an efficiency of 300%. That doesn't sound too good with laws of thermodynamics. So am I missing something here? Yes, of course. Thermodynamics is still there. The fact is that, as I said, the boundary conditions are not actually just this electricity system. There's also comfort level. You are losing temperature, you're losing comfort, therefore you're giving up something else. So when you sum together the electricity you're injecting, but also the fact you're giving up temperature and comfort, you have again a balance of an input and output. You will see that is no longer this kind of strange situations against the laws of physics. So if now just when you look at this, then you realize that discharging must be related to some physical component. So what is the size of the battery? And somehow, as you may I mean, it should be straightforward now to understand that this is really linked to both the characteristic of the building that you have, and as Carmen was showing, you can change, for example, the amount of resistance that you have in your building, so the insulation level, but you can also change somehow the inertia of the building by changing the capacitances, which depend on the size of the building and the materials of the walls and everything else. And then, let me just skip this for a second, it also depends on the potential additional storage that you have. For example, in this kind of study here, we show that changing the amount of thermal storage and buffer, everything else that you have in there, you effectively change the equivalent size of your virtual store in terms of electricity, from electricity perspective, and therefore you can basically provide more and more demand response, considering potentially a lower impact on the comfort. Otherwise, you can again give up more comfort, and then again you allow more flexibility. You somehow enlarge the size of your virtual storage, not because you add thermal inertia or store hot water, but actually because you allow more flexibility in terms of temperature in your building. If you look at our original model about the service duration, that actually links back with what we call the duration flexibility envelope. But instead of the real battery, now you have a building. And again, instead of the energy content of the battery, you now have actually the characteristics of the buildings, including the temperature is in there and the physical model of the building and the comfort level that you have and you want to give up. And then depending on how you change these parameters, the equivalent size of this battery changes. However, the modeling that I've shown in terms of flexibility for the electricity system can be mapped in a straightforward way when you look at buildings. And if you want to do it in a more comprehensive way, what you do is just you model this as a multi-energy node with all the proper equations, and then you have basically all the mathematical models to do this kind of analysis. Now, this is for a building. What happens when I integrate this in a district where I have a group of buildings together? Well, again, there are different ways I can look at this from a flexibility perspective. If I look at electricity and heat, and I start from a base case where I'm using boiler, somehow I'm using a centralized system because it's all based on big electricity networks, big gas networks, getting to house and producing electricity and heat through the boiler. Moving forward, and this is things that are being done more and more actively in Europe in many countries, I really look at a more comprehensive integrated energy systems where I put together, for example, combined heat and power, boiler, electric heat pumps, thermal energy storage that can be used for a commercial center, for a factory, but also, of course, can be modeled as a multi-energy node, but also can be used for multiple houses as a community energy system, as a district energy system. So it's both electricity and heat. You may have a heat network, especially in the northern countries. And then if you imagine a future where this fuel, instead of gas, like it is now, most of the cases, or biomass in some cases, for example, could be hydrogen, green hydrogen, then you really start seeing a system of the future where you're really integrating multiple energy vectors and you are deploying flexibility. Alex will show you later what are the flexibility maps of the system. You will see how amazing the flexibility you can create by coupling multiple devices to provide different energy services. How large the flexibility map becomes and the great flexibility potentials in economic terms. And if you look at this paper, this is actually the first paper that we wrote really looking at all these arbitrage opportunities, the cost-benefit analysis, including investment costs and all that. I can tell you that the flexibility benefits greatly outweigh the investment cost. Even if you have more infrastructure is needed, the savings are so massive that actually it really looks like the right thing to do. And again, this has already been done in many countries, not with this level of complexities, I think, still a bit research-wise. But no, we are moving towards that direction in many countries, including Scandinavia, where Germany, UK slowly. But no, I think it's happening. So okay, but Pierluigi, that this is Australia, not much heat needed. So let's talk about PVs. Okay, so how do you create flexibility in the community when you have lots of sun? How flexible is a system like this? You have a community, and then you have PVs. How flexible is the system? Well, first of all, if each house is really operating individually, as we said, the only flexibility there isn't there is to curtail PV. So you would curtail PV primarily not to harm the distribution network, things that you saw with Nando. So it doesn't really look like a very positive way of using your resources. Yes, there is flexibility, but somehow it's a negative flexibility. You're not using in a positive way. And that's why, so no, not really too flexible. That's why you add batteries, because how flexible is this? Well, say instead of curtailing, because I need to export, I do not have sufficient consumption time when there's lots of production PV, I store it, and then I decide actually when you sell it in case. And then depending on the size of the battery and the strategy that you use, you can think of arbitraging this and making some money, or maybe you give it to a commercial aggregator, virtual power plant, we do it for you. We will see this in the last block. You're certainly introducing flexibility, but do I have other options? Well, there is actually another option that is becoming, it's becoming more and more interesting from a techno-economic perspective, but also from the commercial perspective, which is I add a big battery. So instead of having distributed batteries at home level, I actually add a big battery at a community level, so this kind of neighborhood batteries. And we study how a neighborhood battery that is a shared resource in a local area, if it's a community, it's much easier. There will be some sort of community sense. See if that can bring benefits of flexibility that are greater, also in terms of investment costs with respect to having complete decentralized system where the batteries are owned individually. And actually, we're doing quite some interesting work with the city of Melbourne on this, and there's also an active call from the Victorian government about community batteries. So it's an important topic. I will show you something later if I have time. Otherwise, we also have a Jupyter Notebook exercise later on. It's showing how to do this. And actually, this is only for arbitrage. What we'll show you later is also how to provide frequency control ancillary services with a community battery. When I look at all this kind of constructs in terms of multi-energy vectors, again, electricity, heat, gas, I will go very, very quickly. I will leave the slides, but I will go very quickly on this because I don't really have the time to explain details, and it's complicated. It's a big topic. Plus, there are, of course, the papers you can look at. So when you integrate buildings and imagine that you have not only electricity, but also, for example, heat to share resources, but also gas that is interlinking the system. The question is, how do I model the whole district, the whole community, really considering all the networks and potentially the flexibility that arises from interaction of the buildings through the different networks? Of course, there are different ways of modeling this. One approach is to you start from the coupling technologies that you can have in your system. For example, an electric heat pump is coupling the electric system to the heat system of a building, or it could also be coupling the electricity system to a heat network. If you use a large-scale heat pump to produce heat, and then heat is distributed to different buildings. Or you could also have cooling. So you have a large-scale chiller, an electric chiller, consuming electricity, producing cooling, and then you have a chilled water network that is supply different buildings. For example, in commercial buildings, this is quite normal solution to adopt. Now, what you do is you model again the efficiencies of conversion between one energy vector to another, and each resource we have different efficiency characteristics. This sort of linear resources, linear mapping that I was showing you earlier, and then you need to write the equations network by network. And if the power flow equations are difficult, where the gas equation, everything else, and nothing to say easier than the power flow equation. So we're still talking about non-linearities, non-convexity, and all that. So somehow all that was presented by Steve and Nando in terms of OPF and difficulties with the power flows in the convexification of that applies also for the other equations. And there is lots of work has now been done to understand how what was done for the electricity system. Somehow Stephen was pioneering in terms of convex relaxation of OPF can also be extended to other energy networks. And that's exactly the topic of multi-energy optimal power flow, where effectively what you have now is different buildings that are interacting. There could be a centralized controller, could be different controllers interacting with each other. And then the interaction is through non-linear energy networks. That's a difficult problem mathematically. It's a mixed integer non-linear program in general. When you look at all the options you have in the system, basically there is no way to solve it in a way that we really understand. It's the most non-convex problem that we have basically. So you need to simplify it in different ways. You can use meta heuristics. You use the linearization of the network power flows, so that you can use mixed integer linear programs that we understand much better. You can use decompositions just to breaking down the problems, making much simpler. So you can, for example, decompose into sets of mixed integer and nonlinear programs, but because they are all like easier to solve, they know I can make it because it's just a big mixed integer nonlinear program. That just can't make it. Actually, solvers I don't even understand well how to write the problem in some cases. Or more recently, there are some convex relaxations that are being proposed, again, somehow following the work that Stephen did some time ago that he presented on Monday and Tuesday for electricity system. We did actually develop with Alex, that is going to present something later on, quite a nice and sophisticated tool to do this. And in this, the way that we did the modeling was to basically say, whenever you need to control resources, you can't beat a MILP controller, so a mixed integer linear program, to develop a controller for resources in a building or resource of a sort of community energy center. And then what you would do is you would have sort of the set points developed by your MILP controller. Then you send the set points to a power flow model, not only of the electricity network, every network that you have in there. You have a gas network, a heat network. Your set points would be for each network. Then you run the full non-linear power flow for each network, because we have very efficient ways of doing it, particularly Newton algorithms, especially if the network is not radial. And there's quite some work that we're still doing on this, including in my team at the moment, to develop a generalized theory of a Newton-Raphson solution for multiple energy networks. Now, what you do is you run a MILP, you send set points to the full, the equivalent of an AC power flows, but on all networks. Then does it converge? Is it a feasible solution or not? If not, then you would use a linear network approximation to change the set points, and then you go back to MILP, and then you would iterate until it converges. And if you're familiar with the traditional optimal power flow techniques that are based on sequential linear programming, then this is pretty much the extension of sequential linear program to sort of multi-energy systems. By the way, very recently, I forgot to cite it. Maybe I can put it in Canvas. Very recently, we developed two sequential linear programs, one for electricity only, for both transmission distribution networks, and one for electricity and gas system that are extremely efficient. The one on electricity and gas system that is at the moment run in a project with the Future Fuel CRC, it is run in the real transmission network of Victoria. It basically runs 100 times faster than state of the art, and about 1,000, 10,000 faster than a commercial tool. So you imagine what I'm talking about, like really running full network models, including line pack and all that, the gas network and the electricity network. So it's really interesting. Anyway, this kind of modeling, I think it's the modeling that is coming up in the future. Now, and again, I'm not giving you too many details because the mathematical presentation of this is really is complicated. So I would rather point you to papers, and then for me it's more important you understand the general picture I want to give you. But I would like to now discuss a couple of case studies before I give the word to Alex and we show you some more interesting Jupyter notebooks. So one is the fact that when you look at a building, of course there are, the buildings of the future, and already what is happening here really looks at the controllers that you can have in a building, home management system, and then these are going to interact with other controllers that can be, for example, in a DSO or an aggregator. There would be this interaction of controllers with technical and commercial controllers of other entities. The controller in the building's home management system would now be based on typical characteristics of different appliances that I model here as deferrable or curtailable. And then you have completely deferrable, flexible, non-flexible, curtailable partially or fully. Then there would be some consumer preferences that you can have as an input. And then you can have then an optimization engine that would be looking at the physical characteristics of your resources, the consumer preferences, and then you would, the model basically would come up with some optimal dispatch of the different resources, and the dispatch in this case may be the starting time on non-flexible resources. When you would consume power, you have a flexible resource such as an electric vehicle. What is the power you need to curtail, for example, for an air conditioning system? Or if you have some lights, you can switch on and off. Well, what do you need to do this? And you would do it at the right time also. And then you can have a receding horizon approach. I think Maria yesterday probably presented model predictive control. I'm not sure, I couldn't attend or everything, but this is basically a model predictive control. And if you look at this paper, there is a sort of full formulation, which is also very similar to formulations being used in several projects in Europe that I was participating in. However, all of this comes down, besides the mathematics, it really comes down to consumer preferences and what you can do with these appliances. So really flexibility, even if we do all this mathematical model, that really comes down to what the customers can do. So can do or allows to do. So when you look at this different, again, definition, deferrable, curtailable, and you look at your own appliances, like how would you define the flexibility of the different appliances? Because we can talk about mathematical models and algorithms, we have them, read the papers, I'm sure many of you already would have implemented this also in the real world, perhaps. But actually what matters is what is the consumer allowing to do. So if I was to ask you here to tell me for each of these different appliances, is it deferrable, so it can be shifted in time? Is flexible or non-flexible? So when it's non-flexible, you shift it in time, but once it's started, you can't do it. You cannot interrupt it. Instead, if it's flexible, you can start, interrupt, shift, and go on with the cycle, for example. Or when it's curtailable, it's partially curtailable. For example, an air conditioning system can be modulated, or it's fully curtailable. For example, you can switch on and off lights. If you cannot dim the lights, just on off, be fully curtailable. So how would you characterize this? For example, a TV, is it, what is a TV? Is it, where would you put a TV here? If you wanted to provide demand response with TV, where would you put the TV? Let's see if there is some answer here. So So Marie is saying that TV is non-flexible and fully. So non-flexible and fully curtailable, because this fully refers to curtailable. So non-flexible means they can be deferred. But then, of course, when you cannot switch on TV and then switch off like half TV, for example. It is really on-off, right? TV. So the question is, yeah. So let me say it a bit more. TV fully curtailable is non-flexible. Yes. So it's if you accept to be switched off, yes, it's fine. And then it's non-flexible in the sense that if you switch it off, then you just need to wait basically to switch it on again. Yes, so that's what you would do with a TV. Others would just say that actually TV is not flexible at all, and I will show you later an example when a TV is not flexible at all. Actually, if you have kids, nobody would accept to do anything with a PlayStation. I guess. Some of you maybe would be very glad to switch it off, but probably for kids, this is not the case. And for laptop is the same, right? Although for laptop, because there is a battery there, actually you can switch off the laptop from the main electric system, but because there is a battery. So as you can see, I mean, I'm not so sure that we know exactly where to put what, because it's somehow personal. No, it really depends on how we understand the consumption of electricity and what we want to do with that. And in fact, what I'm going to tell you now, I don't know if you have thought about it, is the fact that any time that you allow demand response, there's always some form of storage. So flexibility is always somehow associated with some form of storage. For example, imagine that you are, the pandemic is gone, we go back to real life, we travel a lot, and then you're just back from a trip, and after 2 days you need to go for another trip, you're very busy, and then of course you need to basically do the washing because basically you run out of clothes, and then you receive a signal, demand response signal from a DSO to basically shift your washing machine. Let's say not to do it today, you shift it 12 hours. Say, look, I can't do it. I need my washing and my dryer done in 6 hours because I need to leave again. However, if you have a big storage, a big storage of clothes, actually you can accept this. Say, okay, it doesn't matter. I give up completely doing the washing. I just take more clothes from the closet. So actually, because you have a big store of clothes, you can afford the shifting and so the demand response. So you have flexibility, your electricity consumption, because you're storing, not electricity, you're storing clothes in this case. Imagine the same way you're having, you're inviting friends for dinner, it's just something sudden, your partner's done this, you didn't know it. And then suddenly, you have no dishes, and then what you do? It's like you need to wash dishes, and again there is a demand response signal to actually switch off as much power as you can and shift all your actions. Like, gosh, these demand response signals arrive all the time when actually I need electricity. Well, I think you understand where I'm now heading to again. What if you have like a big store of dishes? Actually, you don't really care whether you have lots of dirty dishes, because if you can access more and more of these dishes, then it's again you actually enable flexibility. So again, this flexibility is not coming from electricity storage. It's coming from other forms of storage. In a very similar way, we can look at this in terms of energy vector shifting, other form of flexibility. Imagine you got your nice well, there'll be an electric Ferrari in a few years. unfortunately, I have to say, for the ones who love Formula One. But anyway, there will be an electric Ferrari that would be good for other things. And it just put it back to charge, and it takes quite some time to be recharged. So especially if it's at home. So what would you do? What would I do if I had an electric Ferrari and I needed to go somewhere? Where probably I would just take my bike. And again, if you see here, the flexibility in using or not using electricity in this case for transport is coming from the fact that you can shift your energy vector. In this case, the vector for transport is not an electric car; is actually a mechanical bike, and you're shifting from electricity to human power. In this case, and by the way, this looks very much like me, maybe not now, in a couple of years. And then, would you ever store this? I think some of you already said this. Would you store the Euro Cup's final last penalty? This is like 2 weeks, the picture 2 weeks ago. And how would you store this? For example, like the final England-Italy went on at 5 a.m., starting 4:30 a.m. Melbourne time. Do you wake up at 4:30 a.m. to watch the final? Or, for example, and then imagine, by the way, you wake up at 4:30, and then there is your usual demand response signal saying, "Oh, can you switch off your TV, please?" What do? Okay, say, well, I can watch it later on YouTube or some other service, or basically just say, forget about it. I'm not going to do this. So you wake up 4:30 to watch England-Italy Euro Cup final, and maybe it's going on. Maybe it's 7 is the final penalty. Yeah, I think you all know how this ended up. What you do? You can't store this basically. So it's just this is comfort level that you're not going to accept any compromise on. Again, this tells you demand response, as much as mathematical modeling we do, is really linked to the user, and there are things that you cannot give up, like Italy beating England with the goalkeeper, stopping the penalty. The very last penalty, and then again, I will skip this because Alex is going to show this on sort of on a Python on a Python model. I just want to say that again, this flexibility idea is really fascinating. Once again, because it's so linked not only to electricity, but to everything we do, and not only in engineering terms, but also really with sort of social aspects to some extent when we look at demand response. So what I would do now is I would stop for probably 5 minutes to have a short break. I will have a look at a few more questions, and then Alex will give a little demonstration about a Jupyter notebook, where actually we are bringing together all this multi-edge flexibility. And then in the last part, we will cover commercial aspects, market aspects of flexibility. Probably it will go a little bit longer than one, I'm afraid, but I hope you're happy to stay. Otherwise, everything is being recorded, of course. You can also watch it later. So just going to stop now, and I think we can stop for a bit after, and then we can start again in 5 minutes. Okay, thank you.